Hi, welcome back. Sorry, my previous video finished very abruptly, and I was in the middle of explaining something and realized that video stopped. Anyway, let's start from there. What I was saying that there is another philosophy, and that philosophy is basically what's the impact of transition times on that short circuit power, and how different input and output transition times can reduce the short circuit or can increase the short circuit. Let's look into this one, this example. So our CMOS inverter, this is the input we are giving it here, and this is the output. You can see that the input goes from high to low. That means high, that means NMOS was on and this was grounded, so this was at 0. And now what's going to happen is NMOS is gradually in a typical operation when input goes like this, so output will go like that. Okay, actually I should draw this on the output side, because so what happens is NMOS, as the previous, I think this was input, I see. So I think maybe I'm just following the same notation. Probably better if I had done it at the output. So input, um, hmm. Oh, I think makes sense on the input. I'm sorry, I'm just thinking as I'm teaching. Yeah, okay. So think of that. So input makes sense. Input NMOS was already in linear. Now voltage is coming down. So at some point here, then in a normal state, if assuming its output transition is very similar, then it goes from NMOS into, it's already in linear, then it goes into saturation and then turns off when input is less than that VT, right? But in this case, let's we have a scenario where output changes of 0 to 1 or 0 to VDD very slowly. How can that happen? That can happen when this capacitor connected here, like maybe this output is connected to a lot of other inverters, or and there is a long wire connected here which has a huge capacitance. So you will see this type of waveform when a huge capacitance is connected here. Means this time now we are gradually charging this. As we're charging, this is the voltage appearing at the on the capacitor. So you see that since it's a lot of capacitance, the voltage is going to change very slowly. So that's what it indicates. Unless we have such a huge capacitance connected here and we have a situation like this. Let's look into that. What happens now? Now, initially NMOS was in linear. Great, you agree. Typically at around this point, NMOS will get into saturation because output has quickly already changed. Right, so output is normally go like this. So if you look at output and this, and very slowly we made into this situation that okay, VGS is still higher than VT, but our output voltage, since it changes, drain to source is already greater than VD sat, so it quickly goes into saturation. But in this case, output is changing very slowly. So here, the voltage drain is very close to 0. So it hasn't entered into saturation. It still is in the linear region. And as here, look at this. This is the VT. At this point, still it's very low VDD. So that means transistor is still in linear region. And as soon as the voltage drops below this, we don't meet this condition. So VGS becomes less than VT, transistor is off. So you've seen that the NMOS as was in linear and goes into cutoff without getting into saturation. And this can be good for short circuit, means this transistor was not in a saturation region. So it's not going to create a path, short circuit path. But why this is not good generally? Okay, even though it's good for short circuit, I mean this kind of circuit will be delaying things a lot on the next stage. So the delays from this one to other stages will be huge. So we don't want to reduce power at the expense of timing or creating more timing problems. So not a good idea. But you can see the opposite of this one. And input is slow, output is pretty fast. And very quickly transistor will stay more time in the saturation region. So this is a worst combination. But ideally what we want is we want to stay in the middle. We want to ensure that input transitions and output transitions are kind of identical. So we don't have this situation, we don't have this situation. Kind of says so generally that's why you have seen in physical design we will look into it, but there is a limit on max transition time. And we try to keep transition time within certain limits. Sometimes it's not a good idea to have some nodes that are very fast, extremely fast, other kind of slow. So they can create a different situation. That slow here can come in and create a fast output. If a high drive strength, then we can have a higher power. So just it's better to be consistent, have identical within a certain range input and output transition time. So that was all on short circuit power. Should I stop here before I start on? Okay, yeah, let's. Before I start next component, which is leakage power, let's stop it here. And this will complete the first two components of the power. Talk to you next video with the leakage power explanation. Thank you so much.